Hi everyone. This is Andrea Zonca. I work in the scientific applications groups at the San Diego Supercomputer Center, and I will be presenting today a talk on Python for high performance computing. And all the slides and all the material is available on GitHub, so you can see the link at the bottom of this slide, and then I'll mention it again later. So all the slides and the material is available here, and then we are also recording the video, and it's going to be posted later on. If you have any questions, please type them in the chat, and I have some collaborators here that will relay them to me. And yes, so I think we can start. Yeah. Okay, so first of all Exceed sponsored events have a code of conduct. So this is available in the slide, and if you want to know more, there is a URL in this page and all the contacts people. So the first topic is going to be using the Jupyter Notebook on a supercomputer. So in the past, I used to explain everyone what a Jupyter Notebook is, but nowadays it's so widespread everywhere that I'm sure everybody knows about it already. And a very interesting thing is this link for LIGO, where they published in the form of Jupyter Notebooks their analysis of gravitational waves. So this is a really interesting. So you can take a look at something like this. So now it's over, but you basically have a temporary notebook in the cloud, and you can play with their data. And so how does the Jupyter Notebook works? So it's, of course, it's a web application. So it's running, has a server component, then you connect to it using your browser. And let me see, let me get a bigger pointer. Okay, yes. So with your browser, you connect to this, and if you're running locally on your laptop, then you have this web application which is running, and in the backend, all of your computations are actually done by some Python processes, which are normally called kernels. And there's not only Python, but you can have Julia and many other programming languages. And all of the computation is saved in the JSON file. Which is the .ipynb files. And this architecture, so you see the communication layers are using ZeroMQ in the backend and HTTP or HTTPS in the front end. And this architecture is web-based architecture, so it's very works very well remotely. So you can have a server where you have your Jupyter Notebook deployed here, and then you connect remotely with your laptop. So the Jupyter Notebook and the kernels are running on a remote server, and then you connect with your laptop. Just the front end is running in your browser, but everything else is remote. And this is what we are doing on Comet. So now if you imagine that this server is a Comet computing node, we are going to submit a job through our scheduler for a certain amount of hours, and this process is going to get this computing node for a few hours, and on that we are running Jupyter Lab or the Jupyter Notebook. Okay, so let's take a look at how this works. So if you have an account on Comet, you can try to follow along or do it later on. So you can check out the teaching material from GitHub, and then you will notice that here so now I'm logged in on Comet, and we are going to submit a job to execute the notebook. So you see here this file notebook_singularity.slurm. If you want, you can take a look at that also directly on GitHub. So what this is doing is submitting a job. So you see here all this S batch is telling the scheduler what kind of node we want. So we want a single node in the compute partition for 4 hours, and we're going to load Singularity. So Singularity is a way of executing containers on HPC. We have another tutorial on Singularity available in this series. So if you want to learn more about Singularity, you can find more resources. And what we are doing is we have this container that I already created and which is publicly available, so anyone connected to Comet can access this. And it's an Ubuntu container which has all the latest versions of all of my Jupyter tools. And you see that has Anaconda installed, so we're going to run Jupyter Lab with no browser onto a computing node. Okay, so here you see that it's doing Singularity exec. So it is executing this command, this Jupyter Lab, through Singularity, so that I'm not using the Python, the default Python available on Comet, but I'm using my own newer versions. And at this point, you see in the output of my job, I'm going to have it's gonna tell me what's the address of where I can access my notebook. So you see that has a token, so that nobody else can access this. Only people that who has the right token. Okay, and this is going to change for every session. Okay, and at this point you see I have this Jupyter notebook which is running on a computing node on Comet. Okay, so you see I'm connected to Comet 2022, okay, on port 8888. And if someone else tries to access the same URL, they won't be able because it's going to request a token that they don't have. And so you see if, so if we run, for example, hostname, we can show that we are on Comet. Okay, so the interface is running in our browser, but the actual Jupyter Notebook and all of the kernels are running on this computing node. Okay, so we can run, we can execute our Python commands in the Jupyter Notebook. And Jupyter Lab allows us also to open terminals. So you see, this is a terminal. So the particular thing about this terminal is that it's running on the Comet computing node inside Singularity container. Okay, so this is, so if we take a look, for example, at ATC release, so we can find out which is a Ubuntu container. Okay, so this is a terminal. So so it's important to understand the difference between this terminal, which is running in the computing node and inside the container, and this other terminal instead, which is running on the login node. Okay, and here has access to the standard Comet environment. So the advantage of this terminal is that you have access to the Slurm commands. So I can submit jobs from the login node, while I cannot do that inside the container because the container doesn't have access to the Slurm commands, unfortunately. Okay, very nice. Now, now that we have a Jupyter Notebook running, so you see, you can submit the Jupyter Notebook job yourself doing sbatch and then the name of the script, and this is going through the queue. Once the job is executing, the notebook is going to be available for you to connect through your browser. Okay, and then once you have this, you can, once you check that your scheduler, that your job is already running, then you can take a look at the output file that's gonna tell you what is the address of your notebook, and you can connect to that. And in the rest of the tutorial, we're going to use that notebook to execute some data processing directly on that node, or to connect to workers running on remote processes. Okay, so as we talk about optimizing Python for HPC, there are several levels of optimization that we can think about. And the first thing is, which is the easiest thing, is first to get performance on a single node. So generally, when you want to optimize your code, the first strategy is to optimize on a single node and then scale out later on, because it's easier to do optimizations and also do debugging on a single node and then go distributed later on when you really need to. There are a few concepts that are key to understand how to optimize your Python code. And the most important one is the difference between thread and processes. Okay, so by default, if you are running just pure Python code, it's single-threaded. So it can only use one single core of your CPU. So let's say that you have a powerful machine with 24 cores, then you're just going to use one of them, and all the rest of the computing power is going to be wasted. So what you would want to do, first of all, is to be able to leverage all of that computing power. So if you can, ideally, you can, if you have a 24 cores machine like Comet, you can have a 24x speed up just by being able to do that. And there's two ways of making your software being able to use multiple cores. One is using threads and one is using processes. Okay, so you see here on the left we have a process, and a process, we can think about this as a Python process. So this Python process has just one single code. So by default you are in this situation. Okay. And there's two ways to speed it up. So we either go multi-threaded. Okay, so multi-threaded, that means that inside the same process, so this is one single process again, but there are multiple threads that can execute simultaneously. Okay, and so if your code is able to have threads, they share the same memory. Okay, so they have access to the same variables, and so there are some complications. Okay, you are not, for example, that you might have out of order execution. Okay, so you might have, you're not. There are a lot of complications because the threads are not always executing the code at the same speed. So you can have stuff which is processed out of order compared to when you run in a single process. Okay, but if you have a code which is equipped, and we'll show later how you can achieve this, you can have here, you can have one CPU executing each thread. So you are able to go 3 times as fast, ideally.
There's a question about the .slrm extension. Is that just a batch submission job?
Yes, yeah, it's just a text file. And then another way instead is using multiple processes. Okay, so the idea is that we are in the situation on the left here, but instead of having one process, we have multiple processes. Okay, and so at first sight, this should be worse because why? Now you have to duplicate your data because different processes do not have access to the same memory space, and so they cannot access the same data. So each process is going to have their own data, and then you're going to have multiple copies of the Python interpreter. So it's not very efficient. Okay, but there is a problem instead with threading, which is the infamous global interpreter lock. So the problem with the implementation of CPython, of the standard Python interpreter, is that to, there is an implementation details where whenever you are modifying any Python object, so let's say that you are working with strings or you are working with lists, so every time you have these Python objects that are being manipulated, then there is a lock that's put in place by the interpreter, and only one of the threads can acquire the lock. And so the other ones are waiting. So if you have a threaded code which is manipulating Python objects on different threads, then this is not going to get any speed up, because one thread is going to execute at a time only, because that acquires the lock, the others are waiting. Then once that thread is done, then it's gonna release the lock, and another thread is going to process. And this is a big issue with optimizing Python code. Okay, so now this would only work if you have code, for example, which depends on something outside of Python. For example, if you are waiting on network connections or waiting on disk access, then you don't care that much because you're not modifying Python objects, so the GIL is not released. The GIL is not kept too long on each thread, so you can gain speed up. But if you have numerical computation that are very expensive and they are modifying Python code, then this is not a way you can go, and then you need to do multiple processing. Okay, and so for a long time, these were the two ways to go. So either you do multi-threading or you do multi-processing. And so let's take a look. I have an example code that shows you the simpler way of doing multiple threads and multiple processes using the Python standard library. Okay, so you see here I have this notebook, and I am importing the threading module. Okay, so this is part of the Python standard library and allows you to create a thread. Okay, so let's say that what we want to do is we have two functions, one that's reading data. So this is they're just fake functions that just sleep for half a second. And the same thing, the perform computation. Okay. So you see that if you do read data, this is printing out processing as it goes, and then it's taking 2 seconds to read, to pretend that's reading something, and then the other one is performing some computation. It's taking 2 seconds. So we can parallelize this, so we can overlap data reading and computation by using threads. So you see how you would do this. So you create a thread object, and you give it a function, and you give it arguments, and this is preparing the threads, but is not actually executing anything. And then when we want to execute, we call start. Okay, and then if we want to wait for the threads to finish completing, then we call join. Okay, so we start so this is basically starting the background processing of this thing, of this reading data. And then the second start is starting this computation in the background. Okay, and then we could go ahead and do other stuff while they are processing. And then if they are already completed, after a while they can finalize and complete, no problem. But if you want to instead wait for them to finish, because for example we need their results to be available, then you call join. Okay, so this is a very manual way of implementing multiple threads, but it's a simple way. For example, if you want to overlap two different computations. Okay, so we are reading data and performing computation at the same time. Okay, so let's say that you have a big list of files. You can read the first, and then while you are computing the first, you are also reading the second, and then so on. Okay, and the same thing, it's very, very similar syntax if you want to do with multiple processes. Okay, so if you can do with threads, it's always better to do with with threads. So if we are is more efficient. So if you do not have issues with the global interpreter lock, so if you see that you are actually gaining, so the best way to do this is just to test it. So you test with some sample code, and you find out if are you gaining. Do you see that your the speed up that you are expecting is achieved with threads? Then very good, you can keep using threads. If you instead see that you don't have the speed up that's expected, then it's probably due to the global interpreter lock. So your threads are locking, and then at that point, the only way to go is to use multiprocessing. Okay, fortunately, the syntax is very similar. So you import the multiprocessing module, okay, and then you instead of instantiating threads object, you instantiate process objects. And so in the background, this is creating separate, completely separate Python processes. Okay. Okay, so let's see. Yeah. So you saw quickly on the right that we had more lines. So this is actually creating processes, and then they are dying once they are finished executing. Okay, while threads instead you wouldn't see them here because they are not separate processes, but they are contained in the same Python process which is executing the kernel. Okay. Okay, very good. So is there any question on processes and threads? Okay, very good. Ah, okay. Okay, very nice. Okay, okay. So now what I would like, so let's start first with NumPy multithreading. Okay, so a very good, pretty recent news. So in the last maybe couple of years, a lot of the libraries that NumPy is depending on are already multi-threaded. Okay, so this is a great news because without you doing anything, you are going to get NumPy to run with multiple cores and multiple threads, and being able to use multiple cores on your machine very easily. So you see, for example, here we have NumPy, and if we print config and show, we see that this NumPy has been computed with is being compiled with the MKL library. Okay, the MKL library is a library by Intel, which is implementing all of the a lot of math operations that are then exposed with NumPy, and they are implemented already with threads. Okay, and nowadays, whenever you install Anaconda, you already get a NumPy version which is has this capability, so has been able to use multiple threads, and so this is not available on every function. So for example, now you see I'm creating a random matrix, and you see that the CPU usage on the right here got up to 100% and no more. Okay, so 100%, that means that I'm using just one single core. Okay, but other functions instead are multi-threaded. So see that here I'm running this NumPy computation. So you see it's a pretty long computation where we have logarithm, sine, square. So it's pretty intensive computation. When I execute this, if you take a look on the right, you can see that we're going to use multiple threads. So you see here. Let me speed this up. Okay, so we have no time to see anything. Okay, so let's see again now. Yeah, so you see that went up for a second. For a single visualization, it was 2400. Okay, so that means that was using all of the 24 cores on our CPU, and so this is of course a great speed up. So we can get something close to 24x. Okay. And so this is very, very good, because basically you have this capability of executing code very efficiently on a single node, just using straight NumPy. Okay, there is still another thing you should know when you're using NumPy. So even if we are using multiple cores, there is a problem which is very common whenever you're using NumPy, which is creation of temporaries. So temporaries are intermediate results in your computation. So for example, here, when NumPy is calling this computation, is actually creating one array for log A, then it's gonna create another array for sine A, and another array for A square. Okay, so it's gonna use a lot of memory. So if we take a look at on the right at memory usage, okay, you see on the memory usage there can get up to 30, or sometimes I saw 35% memory usage. This is due to the fact that is creating temporary arrays on that. So another very interesting library that is still useful to do single node optimization, so before parallelizing on multiple machines, is Numba. So Numba is a just-in-time compiler for Python. So it's basically doing the same thing that Julia does for its language. And this is compiling on the fly a function to native performance using LLVM, which is a compiler technology. And so let's say that we have this compute B function. Okay, so we have this is the same computation we were doing above, but now I've wrapped it in a function. And the only thing you need to do is you call this njit function. Okay, so JIT stands for just-in-time compiler. That means that's compiled on the fly, so it's not compiling like a compiler that creates a library and then calling the library. Just done everything on the fly. And then N stands for no Python. Okay, so that means that is doing an optimization that doesn't use any of the Python internals, and this is the way to have good performance improvements. Yeah.
It says, will I still see the 2400 if I'm having thread lock issues?
No. You would. So if a thread is, so if you have a global so if you have a GIL, you could sometimes have a little more than 100%, but not a lot more. Okay, because so if all of your code is always modifying Python objects, then you're gonna just get 100, even if you have 24 threads, but one of them is executing at a time, and so you're gonna have only 100. Okay, generally there are some delays, so most of the time maybe you can get to using a couple of threads or 3 threads, so you can see something in between, but generally for sure you're not gonna see 24. Yes, exactly. Yes, that's the only way we are gonna get to 2400 is if we don't have any issue with the GIL. Okay, so so you can call this function njit on the compute B function, and this function is going now to be compiled. And also there is another option, which is parallel equal true. So with parallel equal true, this is automatically going to be multi-threaded. Okay, so the peculiar thing about Numba is that it's not actually using NumPy at all. So basically, you pass a function that is basically calling NumPy just to explain number what are the operations that you want to do. Okay, then Number is going to optimize this and directly call some low-level math libraries directly. Okay, so basically NumPy is our own wrapper to the low-level math library. Okay, so another way to get to those low-level math libraries is Number. So the advantage of Number is memory usage in this case. Okay, so what Number does, so you see it's a little slower. Okay, but uses a lot less memory. So I was doing some testing before, and I saw that Number was using something like 20%, less than 20% memory, while NumPy was using 38%. Okay, so it was almost a factor of 2. Okay, so okay, this is because it doesn't need to create any temporary. So takes this, takes our function, basically creates a loop that takes one single one element at a time, and then does the square, does the sign, does the multiplication, does the log, and multiplies together. So basically, does the thing you would do in C, okay? But just starting from the Python function. Okay, so you give it. So there is a lot of documentation on Number, but it's pretty simple to use, and you can disable it temporarily. So basically, you can do all of your debugging in Python, and then once you are happy with the result, you can call this ngit function, and then this is going to give you most of the time is going to give you a significant speed up. Okay, so you see what we're doing here, I'm calling ngit on compute B, and what I get out of this is an optimized function, and then I call A on that optimized function. I call it and I pass A as an argument. Okay. And the other advantage of Number is that you can do loops. So if you have a computation which is easier to express in simple loops, you know that in Python you should never do loops. So you never do Python loops because they're too slow. So with Number you can. So you can do a Python loop and then turn it. Okay, so I have another example of using Number. So that after that we will switch to distributed. Okay, so this is an example of how you parallelize something with Number. So here I have I'm actually using pandas. So I'm using data frames, and I am doing a group by operation. Okay, so a group by operation takes, so in this array, you see here we have the first column, which is the index. We have our index, which has some pixel numbers, and the value, which is some float values. So it's like the temperature at a specific position in the sky. So what we want to do is we want to sum all of the values that are hitting the same pixel. Okay. And so in pandas, you do a group by operation, and it's pretty expensive. So you see that takes a couple of seconds. And if you want to do, if you want to try and check if Number gives us a speed up, then what you do is you implement it in plain Python. So you see here, this is plain Python, and you are doing a for loop. Okay, and so this is going to be very, very slow. Okay, and you see that what you're doing is you are looping through your values one by one, and then you have your output variable, and then in the index array is going to tell you how where in the location of your at which location you need to write your value. So you see, we do index, we take it one by one, and then at that location we add value. Okay, So you say it's very, very slow. It takes 35 seconds, okay? But then the same function that we tested using pure Python, we can do with Numba, okay? And this is pretty impressive. So with Numba, it takes half a second compared to 2.3 seconds. And this is already pre-optimized code. So pandas is, under the hood, is implemented in Cython, okay? So Cython is another technique, but is more low level, is more complicated to use. So I recommend always to try first and do optimization with Numba. And then only if for some reason Numba doesn't work, then try with Cython. Okay, and you can use the JIT also as a decorator. Okay, so when you define a Python function, you add numba.jit as a decorator, so with hat at the beginning. And so basically this is turning this pure Python function in a compiled function with Numba. Okay, is there any question on this, on Numba? And okay, very good. Now I would like to introduce.
Is there a difference between ngit and hit plus no Python equals true?
No, it's exactly the same thing. Yeah. So ngit is a shortcut because most of basically all the time you want to do Numba with no Python equal true, because with no Python equal false, you don't get much speed up. So you defeat the purpose, I think, most of the time of using Numba. But there might be some specific corner cases where you can benefit from that. But 99% of the time you want to run with no Python equal true, which is the same thing as ngit.
Marty's asking what happens if no Python equals true cannot compile.
Yes, that's one of the main reasons why you're using no Python equal true, because it's then gonna give you an error, and then you can understand what's the problem. Okay, so generally you do not want to pass any Python objects, so you cannot have classes. NumPy arrays are fine. Lists, you can also use lists. But no other Python objects. Okay, so basically you run with no Python equal true until and debug all of the errors that Numba is going to throw, and until you have no problems compiling with Numba. Okay, so with Numba, what you do, you generally want to optimize your inner loop. Okay, so as we did here. So we do not want huge functions in Numba. So what we want to do is just the most expensive piece of code we want to optimize with Numba. Okay, everything else, leave it in Python. Okay, when you really need the performance, so you know that your maybe you do some profiling. You understand where your code is low. Yeah. No. It's working. Yeah, it's also working with X-ray. Yes. Okay. Very nice. So now the main thing that I wanted to introduce is Dusk. Okay. So basically, we saw now some ways of doing single node optimization, but now we want to go distributed. Okay. Still, there is Dusk gives you a lot of possibilities, and one of them is so let's okay. So first of all, Dusk, basically what Dusk does is allows you to, so at the core of Dusk, there is a scheduler which is based on a direct acyclic graph. So basically you describe a computation to Dusk, and then Dusk is going to take your array and split it into chunks Okay, so you see here, you remember the computation that we did before. Okay, so this doesn't need Dask because fits in memory. Okay, but still, still we can use this just as an example. So what you do is you have your NumPy array, and then you define a size of chunks. Okay, there is, I think there's also a way of having Dask automatically choose the chunk size for you. But if not, you can just test with different chunk size and see which one works the best. And then Dask is going to execute in parallel. So you see that we are using 2400 percent CPU. So we are using all of the cores. Okay, but it's taking significantly longer. I think that the problem is that we have too many blocks. Okay, and so it's not very efficient in this case. Okay, but we could try to optimize the chunk size and get a little more performance. Okay, but we don't need to do this because if we are on a single machine nowadays, NumPy is already doing multi-threading, so we don't need Dask in this particular case. But it's interesting that I had this example a couple of years ago, and a couple of years ago NumPy was not multi-threaded, and so I was showing this and having a big improvement from NumPy to Dask, but the ecosystem is moving pretty forward in these issues, and now NumPy is extremely efficient in this case. Okay, but the first usage you can get out of Dask is to do computations on data which is larger than memory. So the problem with NumPy is that you always need to have your arrays in memory. Instead, Dask can take care of creating and in computing, basically do computation in chunks. So you see, for example, here we have this AA matrix, which the size is 150 gigabytes. Okay, so it doesn't fit. Comet has 128, so this is way too big. There's no way you can process this on a single node with NumPy, but you can do this with Dask because it's going to create this chunks. So you see it's creating chunks with ones. It's creating just a bunch of chunks, and then it's processing them, then is accumulating those in the sum, and then is doing compute. So you see another feature of Dask is that you need to call .compute at the end to trigger computation. So any operation you do before then is not actually executing, is building this acyclic graph to understand how the tasks can be executed in the best way, and then at the very and then when you call compute is actually submitting all of the computation. So you see here I'm using 4 workers, so you see that CPU is 400%. Okay, so you can choose the number of threads that you're using. Okay, and this also works with files from disk. So there is this other example in the Dask tutorial folder. Okay, so you see here we have a very large file which is random.hdf5 on Comet, and what we could do is we want to compute the sum of this. Okay, so we can even implement it in pure Python, but you see there is a lot of but it's not easy. Is basically I'm going through the file in chunks and then accumulate the sum on this array. Okay, and this is not very efficient. Okay, and what you can do with Dask is, you see you have this this from array, and this from array works from a NumPy array, but also works with anything that has the same interface of a NumPy array. Okay, and in this case, HDF5, an HDF5 dataset, you see you access a dataset like this. So you open your HDF5 file, and then you say that you want the X data set, and the data set has the same access patterns of a NumPy array, so you can call from array. And so this is very good because you can process data on disk, which is larger than memory. So you can process 1 terabyte of data because this is just loading a piece of data each time. So you see that here I'm calling sum, but it's not actually computing anything. So the result is a Dusk object. So it's a Dusk array object. But then when you run compute, this is actually performing the computation. And okay, and you can have much more complicated operations, okay, and this is going to allow you to process data larger than disk, okay? Okay, very good. So another thing that you can do with Dusk, still on a single machine. My notebook is stuck. Just a second, I'm gonna reload the notebook. Another thing that you can do is you can overlap two different operations using Dusk delayed. Okay, so basically Dusk delayed is one of the low-level functionality of Dusk. So for example, this is the same operations we were doing before with threads and with processes. So you can do it also with delayed. So with delayed, what you do is you get a function, okay, and you call dusk.delayed on that function, okay? And now this function, you see that's lazy, so it didn't actually perform any work, okay? But is also asynchronous, okay? So now now those two functions are executing simultaneously. Okay, so you call dusk.compute, so that's the other way of calling of triggering computation. So instead of calling .compute on a Dusk object, you call dusk.compute and you give it a list of objects. You give it all the objects, and then you see you can either use the threading scheduler or the processing scheduler. Okay, and this is going to basically do under the hood the same thing that we did here. Okay, without this calling start and join. Okay, so I think the interface is a little easier using Dusk delayed. Okay.
So we got one question: why would you use dask versus MPI for Pi library that can also work across nodes and distributed?
Well, yeah, MPI for Pi is extremely low level. So if you are already if you're already familiar with MPI, then that's perfectly fine to use MPI for Pi. But if you are running, if you are a new user of HPC, I recommend to try Dusk. Dusk is way easier to learn and to run and to debug, and there's also better documentation. Okay. But if you are already familiar with MPI, then yes, I think also MPI for Pi is a great choice. Yes, and Dusk is automatically going to handle all of the dependencies. Okay, so for example, I have some trouble here. Okay, I have an example in the other folder where I have two computations and with dependencies. Okay, so basically you just do the same thing you would do serially, and Dusk is going to automatically handle dependencies. So you see here we have two functions. Okay, so you see one which is incrementing by 1, and the other one is adding 2 values. So you see here we implement, we give 1, and then we call increment, okay? And then we do the same thing with y, and then we call z that depends on the output of x and y, okay? And this takes 3 seconds because each of those functions, they have a sleep of 1 second, okay? So I'm running one, the other, and then the sum, okay? If we have delayed, you see that now we turn everything into delayed objects, and now we give it basically to Dusk to handle, okay? So what this is doing is what this is doing is okay. What this is doing, you see, that's taking only 2 seconds because understands. So under the hood understands that the two things can be executed in parallel. So you see, if you call z.visualize, this is printing the Dusk acyclic graph that Dusk is computing under the hood. Okay, so you see that understands that these two parts can run in parallel, and then after that we can go into add. So here is basically chaining all of your dependencies and doing the best parallelization that it can automatically. So as there's a lot more automation into this than lower level tools. Okay, okay. So now let's go back to here and go to the multi-node. So what happens instead when you have multiple nodes? So what we can do is we can what we can do is, one way is to use Dusk job queue. Okay, I have some documentation. I have some documentation for Comet that you can. So you see there is a link on this notebook, and unfortunately we cannot use it right now because we are running inside the container. And inside the container, we do not have access to the Slurm commands. Okay, so let's say, so we need to do it manually, but it's good we understand what's actually happening. So you see, if we first launch the scheduler, so the scheduler is a separate Python process which is basically coordinating all of the workers. So you see that this scheduler is running on the same node which is executing the notebook, okay? And then we can get out of that and back in the computing node, and in the computing node we can launch some workers, okay? So this is a separate Slurm job, okay? So if we take a look at the content of this Dusk worker, so you see that is using again the same image, singularity image, and then it's running so that everything has the same version, and then we are running, we are getting 2 nodes for 20 minutes. Okay, so those 2 nodes, and then on each of those nodes we are running 1 worker. So you see that I'm telling the IB run. So IB run is handling the spawning of the processes on the different different nodes, and I'm telling it just to use 1 worker per node, okay? Because then each worker can use multiple threads. So I'm gonna have 1 worker on each node, and each worker is gonna have 24 threads. So at the end we will be able to run 48 processes together, okay? And then launch worker, you see, is calling Dusk worker, and is telling it to use just 1 process. Okay, 1 process, but 24 cores. Okay. Okay, so now we are waiting. So we are waiting for, you see that the work, you see that this is a separate job which is pending. And in the meantime, we can take a look at the Dusk dashboard. So it's a very nice feature of the Dusk distributed scheduler is that you have you have a UI. So you see here, we can see all the workers that are connected to our scheduler. So currently, you see we don't have yet any worker connected. And then important visualization tool is the task stream. So here we basically will be able to see for each row. So we're going to have 48 rows, so it's one row for each thread, and then we are going to take a look at exactly what each process is doing. Okay, so let's take a look at how we do this. So we first we connect to so first we sorry, I lost my window. Okay, yes. So we from distributed import client. So you see the distributed gives you access to the client. So the client is running inside the Jupyter Notebook and is connecting to the scheduler. Okay, and then is dispatching work to be executed by the scheduler. Okay. And so you see, Dusk works exactly the same way as it runs on a single machine. So we can create matrices, and so these matrices are not going to be created on this inside this process, inside the notebook process. It's just going to use the here are the workers coming in. So the job started, we have the workers available. Okay, and now you see we create those objects. Okay, so we are processing 300 gigabytes, and then we can call compute. When I call compute, I switch to the Dusk UI. So you see all of those processing. Okay, so you see here you can understand what's going on. So you see that if you over this, you see that this is one sum. So basically it's summing the ones. And the important thing you see that's red is data transfer. So you want to always minimize. One of the slower thing about distributed computing is transferring data. So so what you can understand the performance looking at this plot by looking first that all of the processes are doing something. So you see there are 48 lines, each of them is doing something, okay? And then you do not have too much communication, okay? Of course, we need some communication, okay? Because we are, you see, we are accumulating this sum. And so we are doing the sums process by process, but then we need to communicate those results and accumulate all of them until we have the last result. So you see there is some communication here and there, but after looks like the efficiency is pretty good. Okay, and so we can take a look more at Dusk Graphs. Okay, so you see how even simple so you see simple computations like this. So you have just understands that you are producing, this is an array of 15, just an array of 15 elements, and they're all ones, and we can split them in chunks of 5. Okay, and then as you accumulate more processing, more math, the acyclic graph is gonna get more and more complicated. Okay, so you see if we do +1, then this is still totally independent. Okay, so you see they never mix up. Okay, but then if you do, for example, a sum, then you see that there is an aggregate. So now Dusk understands that can use 3 threads for doing this 3, and then once gets here needs to do some communication, and then on one only process do the aggregation. Okay, and this gets very complicated quickly. So let's say that instead, if we have a matrix, and then for example here we're doing the transpose. So you see there's the diagonals that have a different processing than the other elements that are more complicated, and so on. Okay, and okay, and gets more and more complicated. And but the good thing is that all of this is done under the hood. So Dusk is going to try to optimize your parallel computation as much as it can, and you can generally what you want to do is you want to start from an so if you're analyzing data, you want to start from an HDF5 file, which is very pretty efficient to access distributed, and then Dusk is automatically processing just single chunks. And for example, if a computation is very complicated and needs to read again from disk, maybe, then that could happen as well. It's all being done automatically, and you can dig deeper by looking at dashboard and looking at this exactly to understand exactly what Dusk is doing. But and the same thing when you want to output. So you have processed your files. You want to write everything to disk, and then also that can be done in chunks. Okay. Okay. For example, yes, this is one. Okay. So you call to HDF5, and this is going to write this to file. Okay, and this is never going to first create the complete array in memory. Okay, it's just processing one chunk at a time, in parallel, of course, a few chunks at a time in parallel, and then doing all of the processing in parallel, and then write to disk. Okay, and the good thing is that so Dusk has great documentation. Okay, if you look Dusk PyData, okay. And also, if you use, for example, data frames, if you use pandas, this is a very good upgrade scaling path. So you start using pandas data frame in a single code, in this just in a single machine, and then when you want to scale out, you switch on using Dusk data frames. Okay, so Dusk data frames have a lot of the same interface of data frames, but they run in parallel. So and under the hood, this is still using pandas data frames. So what it is doing is going to create small data frames. So instead of having chunks, as we saw before with arrays, here we're going to have small data frames, and Dusk is going to take care of handling all of those data frames and do the right operation on all of those data frames, and then accumulate all of those operations to have a global global processing of your file. Okay. Okay, very good. So we are on top of the hour. Is there any question? Okay. Very good, thank you. So you can find all of the material on GitHub. So on I'm gonna show you the URL again. Okay, yes, so if you find any issue executing this, you can open an issue on this GitHub repository, and I'll answer when I can. And thank you for participating. Do we have any announcement?
No announcements. There's one last question. Are there any good resources that discuss the scaling of dask for common tasks? Good resources for the scaling of dask. Discuss the scaling of dask for common tasks.
Yeah, the only resource I would say is the documentation. There are some performance tips. So there is a section in the documentation about performance tips. That's a good starting point. Yeah, and it's is often useful to use these technologies together. Okay, so for example, you can use Numba to have very good very quick functions, and then you can execute them in parallel with Dusk. Okay, so you can have the single node optimization and lower memory footprint of using Numba functions, and then on top of that, you can scale to multiple nodes with Dusk. Okay. But generally, the good thing of Dusk is that a lot of parallelism is described at very high level. So what you tell Dusk, the difference between using Dusk and using a lower level tool like MPI4Pi is that in Dusk, you are describing the computation at very high level so that you give freedom to the library under the hood to do a lot of optimizations for you. Okay. Instead, in MPI4Pi, you are more in control. So can be an advantage if you are an expert, especially. But if you're not an expert, it's a lot more complicated to get good performance. Okay, out of a low-level tool. While let's say to have decent performance out of a low-level tool. Instead, you have a high-level tool, so you can combine two very high-level tools like Numba and Dusk to have very good performance gains with not too much effort, because you're still writing Python. The APIs, the interface of the tools are pretty easy, and you can switch back and forth between normal Python and optimized code easily.
That's great.
Okay. Thank you very much. So also the recording is going to be available. So if you want to go over it again. Thank you.
Thank you, Andrea. Thanks, everyone. Bye-bye.